Hi, this is Jacob Beauchamp, and this video I'll be going over my final project for the game engine design class. So this game, as a bit of background, is a 2D kinematics puzzle. So this is designed more or less to be like, say, for high school students, just a bit of interactive practice for doing some 2D kinematics problems. So these will all be Newtonian physics, no calculus based. None of that. So this is again for like high school age. So the problems are relatively straightforward, but there still is some interactivity and fun in here. So let's get to our first example. So we have a cannon and our cannonball over here right next to the camera. And off there in the distance, there's a red box on top of a stand, and that's what we want to hit. So, and in addition to visually seeing that, we have in this problem window, we have the graphical representation of the problem with a bit of specification, like the distance, the launching velocity, time, but we also have the word problem for it. So as it says, the target is at 160.62 meters away. Our cannonball will fire at 40 meters a second, and the trajectory should have it in the air for about 6 seconds. And so this box here requires us to check, or it requires us to enter what the elevation should be in degrees. So if we go in here, I'll enter an incorrect answer first. I have all the correct answers written down, so let's just try something. It's not right. 25 degrees. As we can see, it tells us that's incorrect. And after a couple seconds here, that prompt will just go away, so it's not just sitting there forever as it's gone. Now, if I enter 50, which is the correct answer in this case, it'll say correct, and we can see this UI over here has changed, where now it lets us modify a few parameters such as the gravity scale, air resistance strength, and the elevation. So those are all relevant, more just to the elevation is relevant to enacting the actual problem if they want to just replicate it in the actual simulation. The other two are mostly for fun, like the gravity scaling. Nothing really in the problem specifies that. It's just assumed you're using standard Earth gravity. Air resistance in the problems, it's assumed to be none because most high school level kinematics problems, air resistance is never really a factor. And again, air resistance, that would get into calculus-based physics because as we know, that's related to velocity. So that has to be updated every frame. So the way we handle the air resistance here is just a constant newtons per second force applied, over the x direction. So only in the horizontal. So, and that's again just for fun. So let's start off by enacting the initial firing plan. So elevation of 50, and we launch. As we can see, the camera, first off, the cannon also plays a nice sound, and the camera will follow the projectile as it moves to the target, and as we've struck it here. After about 12 seconds, the cannonball and the camera will go back to the original position they were at. Alternatively, you can manually click reset here. For instance, if you make a particularly bad shot and you can tell, oh, that didn't go where I wanted it to. Let's say I'll set the elevation to -5. That's obviously not going to where it needs to be, so I can just reset. Also, bonus points if you're able to recognize that sound. So let's see. Once we've solved that problem, as it stands right now, and it seems fair enough to just leave it, that you can select the level at any time, whichever level you want. Obviously, there's a natural progression of difficulty, but if you wanted to just skip right to level 5, the program doesn't stop them from doing that. It didn't seem necessary. So that design change was made to just let the user freely select the level. Now, for this problem, here we have another example. Similar problem to the first, but we're asked to calculate some different parameters. This time we're calculating the distance and the time in flight, which again, I have these written down. So 5.58 seconds and 119.48 meters. We can check that. Answer's correct. And the problem specifies elevation of 20 degrees. So here we go. And as we can see, we've scored a direct hit. Now we can do a bit of demonstration since this is a longer shot. Let's turn up the gravity scale to 5.0. As we can guess, this is not going to get anywhere near the target stand before it hits the ground. And we would be correct. Not even close. We've already hit the ground. If I change that to 0, it should never come back. Yep, we're just going up and up, as to be expected. Now I'll turn it back to 1. So the projectile weighs about 25 kilograms. So it's fairly heavy, but let's suppose I'll just go a little overboard here and have the air resistance be 5 kilonewtons per second. Way unrealistic, but that should still that should affect the projectile fairly well. And we can see there that it came quite a bit short. Still a pretty heavy projectile, so it would take quite a few seconds at this angle and that. Since the let's see, the problem specifies the launching velocity is 80 meters per second. Yeah, it would take quite a bit of time to decelerate that, even at that high force. But we could see that there it still came quite a bit short of the actual target. Now let's take a look at the third scenario. This one's one of my favorites because it's you have to do a high angle shot because we're firing right now over this wall. So the wall is the wall is immovable, so we can't just brute force by going straight through that. That'd be funny though. So let's see. The target's 35 meter or 35.31 meters away. The wall is about 15, but that's not really relevant to the actual data we're given, because we need to calculate the trajectory. Since we know the flight time, there's only one possibility here. So I'll go ahead and enter the data. We have an elevation of 60 degrees. And the velocity is going to be 20 meters per second. Check the answer. Yep, get correct. So let's try 60 degrees. Pops the projectile up into the air, and we get a direct hit. Nice. And as we can see, if I set the elevation to 0, yep, the wall is indeed immovable, and yeah, that's not going to work. But points for effort. For the fourth problem, this one we're firing into essentially a valley in the distance. So we have to sort of go in along the slope. To do this, the correct value for the elevation is 19.78 degrees. So let's do that. And we can see we score another direct hit. For question 5, it's sort of the opposite scenario, where instead of firing into a valley, we're trying to hit a target that's up on a hill. And as we can see, in addition to obviously the problems are quite different, each problem we have a hint here that I added. And several of them, for instance, this one just says, because this is similar in a lot of regards. A lot of kinematics problems are like this, where one will be, you use the same fundamental set of equations. This one will use the same equations as problem 3, it says. The main thing is, if you're familiar with the delta S equals V naught times T plus 1/2 AT squared equation. It's essentially that, where except instead of delta S being 0 like it was in previous instances, since the height changes, that's non-zero. And that's one thing we specify in the thing here by saying don't forget to consider the height difference. So 44.7 for the velocity. Check that. It's correct. And now we can fire our last shot. And there we go. One final direct hit. Anyway, that's the gist of this project. Just a fun little interactive kinematics puzzle that can help give students a bit of practice in messing around with all the equations and goodies involved in 2D projectile kinematics. As for the cannon sound, bonus points if you're able to guess barotrauma of the game. Anyway, that's all I have for this video, and thank you for watching, and have a nice day.